All right, my MathCounts people, here we go. We got warm up number 5 from the 2026 problem set. So remember, these are no calculator problems. As per usual, I'll read the problem. You should probably pause it if you haven't done the problems yourself, and then unpause it when you've tried it and look at my solution. Here we go. Number 71. A right triangle ABC has an interior side lengths with AB is 20, AC is 25. What is the least possible area of the triangle? Now they say the least possible area because there's two ways you can actually do this. If we have a right triangle and we're doing the area, we would just do 1/2 the base times the height. Now, if we've got side lengths of 20 and 25, we could have this side as 25 or 20. Let's do that because it's smaller. And this side is 25. In this case, it would be 1/2 of 20 times 25. Half of 20 is 10. 10 times 25 is 250. All right, but that is not the shortest or the least. The least possible area of it. Just someone's knocking on my door. Just a second. All right. Sorry, random people just came by. All right, so that's one way we can do it. That's not the best way. The best way is to make the hypotenuse 25. Now, I can't find the area using the 25 and the 20 because we have to use, when we're doing base and height, they have to be perpendicular to each other. So I still need to find this side. Now you can use the Pythagorean theorem if you want to, but this is a Pythagorean triple. This is 5 times 5. This is, what did I do, 4? 5 times 5. This is 4 times 5. So what we have is a 3, 4, 5 triangle where everything has been multiplied by 5. So this height over here is 15. Because it's a 3, 4, 5 triangle where everything has been increased by a factor of 5. So this is the best way to do it. It has the least possible area because we have 1/2 of 20 times 15. So half of 20 is 10. 10 times 15 is 150. So now we have 100 less square centimeters. So that one would be the best. The best. All right, next. If x and y are integers and x plus y equals 20 and x over y equals 3, what's the value of x minus y? Well, we should probably find out what x and y is. What I would do first over here is multiply both sides by y so that we get x is equal to 3y. And now I can substitute. In this equation, instead of x, I can now plug in 3y. 3y plus y equals 20. So that's 4y equals 20. Okay, so y is 5 because I'm going to divide by 4 on both sides. Now I just need to find out what x is. Well, x is equal to 3 times y. Y is 5, so x is 15. So the difference between x and y would be 15 minus 5, 10. Next, a numeric palindrome is a positive integer, not ending in 0, because you can't have 0 at the beginning, that reads the same forwards and backwards. For instance, 3, 55, 17071, they're all palindromes, so they're the same backwards and forwards. What is the least palindrome that is divisible by 12? Okay, so the least palindrome divisible by 12. Now 12 is 3 times 4, and 4 is 2 times 2. So 12 is 3 times 2 squared. Okay, so I need to find a palindrome that 3 will go into and 4 will go into, or 2 squared will go into. So the rule of threes for divisibility by 3 is that the digits have to add up to a multiple of 3. The rule of fours is the last 2 digits have to be divisible by 4. So I'm going to look for a palindrome where the digits add up to a number divisible by 3 and where the last 2 digits are divisible by 4. Okay, so it's obviously not any of the two-digit palindromes like 33, 44, 55. 12 doesn't go into any of those two-digit palindromes. So then I would move on to the three-digit palindromes. Now, I can't use any of the ones that start with 100, like 101 or 111 or 121. I can't use those because I have 12, which is an even number, and that means the last number has to be an even number because 4 has to go into this, right? So where I would start my palindromes is at the 200s. So let's start with 202. So 3 doesn't go into this because 2 plus 0 plus 2 is 4. 3 doesn't go into 4. So let's try 212. Well, that doesn't work. That's 5. Let's try 222. Okay, so here's a palindrome that 3 will go into because 2 plus 2 plus 2 is 6. However, 4 does not go into this because 4 does not go into 22. That's the rule for divisibility by 4. All right, so I have to keep going, but I'm going to skip 232 and 242 because both of those are not going to add up to a number that 3 goes into. My next number that 3 can go into would be 252. 2 plus 5 plus 2 is 9. 3 goes into 9, so 3 has to go into this number. Okay, and then I look at the last two digits. 52. Does 4 go into 52? Yes. So now I have found my number because 3 goes into it and 4 goes into it, meaning 12 has to go into it. And so my number is 252. Next. In the capital of Mathlandia, oh, that must be a magical place, a building known as the Gauss Monument, which prominently features a regular heptadecagon, a 17-sided polygon. A scale model of the Gauss Monument is 3 feet tall, with one side of the heptadecagon measuring, I said that pretty good, measuring 2 inches. If the real heptadecagon has a perimeter of 510 feet, how tall is the actual Gauss Monument in feet? Delicious. Okay, so the model is 3 feet tall, and the side lengths are 2 inches of the model heptadecagon. Okay, so that's the model. The real heptadecagon has a perimeter of 510 feet. Okay, so perimeter, if there's 510 feet in the perimeter and there's 17 sides, then that means the real perimeter is, or not the real perimeter, the real side length is 510 divided by 17, 30. And that's in feet. So now I need to compare it to inches because over here in the scale model here, I'm in inches, so I need to compare it to the actual heptadecagon, which is 30 feet. So 30 times 12, this is to convert it into inches, that comes out to 360 inches. All right, so I've got the model compared to actual, which will give me a scale factor here. The scale factor is 2 over 360, or 1 over 180 as it reduced to. So the actual is 180 times the model. That's what this scale factor is telling me. So if I want to know how tall the actual one is, the height of the model is 3 feet, and we want our answer in feet, so this is delicious. Now all we have to do is multiply the model times the scale factor of 180, and 3 times 180, 540. It's pretty tall. All right, next. What is the sum of 123 base 4 plus 1,234 base 5 written in base 10? Well, let's look. So, my first number is 123 in base 4. My second number is 1,000, that was too big, 234 in base 5. So in base 4, this number is keeping track of the 4 to the 0 powers. This is how many ones you have. This number is keeping track of how many 4 to the first powers you have. So we have 2 4s. This number is keeping track of how many 4 to the second powers we have. So this is keeping track of how many 16s. So in base 10, 123 base 4 is actually 1 times 16, 16, 2 times 4, 8, 3 times 1, 3. So 16 plus 8 is 24, 24 plus 3 is 27. So 123 base 4 is actually our number 27, because we do all of our counting in base 10 because we have 10 fingers. Now base 5, this is keeping track of 1s, this is keeping track of 5s, this is keeping track of 25s, and this is keeping track of 125s. So these are the powers of 5. So this, 1 times 125 is 125. 2 times 25 is 50. 3 times 5 is 15. And 5 times 1 is 5. So we got 175 plus 20, 195. So 123 base 4 is 27. 1,235 base 5 is 195. We just add those two numbers together and we end up with, wait, did I do something wrong? No, I didn't do anything wrong. Everything's great. So we end up with, am I looking at the right problem? Oh, I did write it down wrong. This is a 4. Dang it. All right, that's me trying to talk and write at the same time. My bad. So this is a 4. I was like, why is this coming out as the problem when I practiced it? Anyways, so we got 27 plus 194, that's 221. Ugh. All right, number 76. The sum of the first 5 positive perfect squares is equal to the sum of the first n positive integers. All right, the first 5 perfect squares are 1, 4, 9, 16, 25. 1 plus 4 is 5, 14, 30, 55. All right, so 55 is what the sum of the first perfect squares are. And now we want the sum of the first positive integers. So it is really helpful for you to know, like when you add up numbers, like the first 4 numbers is 10, then 15, then 21, then 27. You do this a lot with adding a bunch of numbers. So I just happen to know, especially because I like to do puzzles, cross-sum puzzles. So the first 9 numbers add up to 45, and the first 10 numbers add up to 55. So it's helpful to know little pieces of information like that. So the first 10 numbers, if you add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, that comes out to 55. And that's just because I play cross sums that I know that. You should play cross sums. They're really fun. Here we go. How many positive 3-digit integers have a hundreds digit and a units digit that are each either 1 more or 1 less than the tens digit? Eugh. This is the worst. All right, so we've got some things here. Hundreds, and then we've got 900s. And then we've got 2, 3, 4, 5, 6, 7, 8, all in between. And the reason why I've done it like this is because these numbers in between we're going to see have the same amount of possibilities, but the numbers on either end have less possibilities. Okay, so we've got how many 3-digit integers have a hundreds digit, so the first digit, and the units digit, the last digit, that are either one more or one less than the middle number. Okay, so looking at the hundreds, if this is 1, and it's 1 more or less than this one, we can do 1, 0. And then this one has to be 1 more or 1 less, but I can't get less than 0. So 101 would work. These are both 1 more than 0. But we could have also done 1, 2. And then this last one can be 1 less than this and be 121. Or it can be 1 more than this and get 123. So for the hundreds, there are 3 ways to do this. We could go 1 and then go below 1, but then that only means I can go above 1 because we can't go below 1. But if I do 1, 2, we can do 1, 2, 1 or 1, 2, 3. Now, in the 200s, 300s, 400s, 500s, 600s, 700s, and 800s, they're all going to be the same. So if I do 200, I can go below and then above, or I can go 2, 1, 0. So 2, 1, 2, so down, up, or down, down. Or I could do 2, 3, so that this is 1 more, which means I could go 2, 3, 2, or I can go 2, 3, 4. So there's 4 ways to do it. So you can do the number below and you get 2 ways, or the number above the first number and get 2 ways. So there's 4, and that's going to happen for all of these. All of these numbers are going to have 4 ways to do that. So there's 1, 2, 3, 4, 5, 6, 7. So 7 are going to have 4 ways to do it. That's 28 different combinations. I got 3 from the 100s. From the 2 through 800s, I get 4 for each of those. That's 28 more. Now the 900s is a little bit different. I can do 9. I can't go above 9, so I have to go below 9. And then, wait. Yeah. And then my other option is 9. So we've got a total of 1 for this one. So that's 3 plus 28. That would be 31 plus 1 more. Did I do that right? Yeah, 32. That's the right answer, right? Yeah, 32 is the right answer. I think I did it right. I don't know. The answer is 32. I'm pretty sure I did it right. We're running out of time. Let's hurry up and finish. All right, it takes Corey 14 minutes to put frosting on 2 dozen cupcakes. So his rate is 14 minutes for 2 dozen. So he can do 7 minutes and 1 dozen. Okay. Next person, Dory. So this is Corey, this is Dory. 15 minutes to put frosting on 3 cupcakes. So that would be 5 minutes per dozen. All right, there's their 2 rates. If they work together to put frosting on 1 dozen cupcakes, how many of the cupcakes will Corey put frosting on? Okay, so let's see how much time it's going to take to do 1 dozen cupcakes. So he can do 1 dozen in 7 minutes. That means in 1 minute, he can do 1/7 of the job. Dory can do the whole job in 5 minutes. So in 1 minute, they can do 1/5 of the job. And then together, in 1 minute, they can do 1x of the job. I'm now going to multiply everything by the common denominator, which is 35x. So I'm going to multiply both of these by 35x. I end up with 5x plus 7x equals 35. So I multiplied everything by 35x. This means 12x equals 35. And then divide by 12, we get 35/12 of a minute. That's how long it's going to take them to work together to do both. Now this one says, how many cupcakes will Corey put frosting on? So Corey can do, this guy, 12 cupcakes for every 7 minutes. Now, if I use this is minutes. So if I want to know how many cupcakes to cancel out minutes here, I would multiply by 35 twelfths of a minute. Minutes cancels, and then this tells me how many cupcakes he's made. And it's really nice that this all reduces nicely. 7 goes into 35 5 times, 12 and 12 reduce. It looks like he can make 5 cupcakes. I'm really starting to wonder if I did this problem wrong. I got the right answer, but the more I look at it, I'm like, did I do it right? I don't know. I got the right answer the first time I did it, so I'm just going to go with it. Maybe I should look up what the actual solving is. What is the absolute difference between the mean and the median of the 5 numbers? Well, let's see. This is the median. So the median is 11. Let's find the mean. We add up all the numbers. 7, 18, 18, 32, 32, that's 55. There are 5 numbers. So the mean, mean The mean is 11. So the median and the mean are both the same number, so the absolute difference between them is 0. They love putting 0 as an answer. Last one, Garrett's passcode has 4 digits. He knows that the digits are 2, 6, 8, and 7, but he cannot recall the proper sequence. What's the probability that he will enter the correct passcode on his first try? All right, so we have 4 numbers, and none of them are the same. How many ways can we order 4 things that are not the same? That would be 4 factorial. So there are 4 times 3 times 2. 24 ways he can do this. So what's the chance that he's going to get it right the first time? 1 out of 24 ways. 1/24. The end. All right, see you guys later. Math hard. Bye-bye.